Hello guys, let's solve another classic coding problem today, which is twosum. This problem has many variations with or without sorted input. Some just need true or false answer or some specific information, but I'm gonna stick to the official Leetcode description now. So, like the problem says, we're adding numbers together. It sounds pretty straightforward, right? Given an array of integers, nums, and an integer target, we have to return the indices of the two numbers such that they add up to the target. We also may assume that each input would have exactly one solution, and we may not use the same number twice. And we can return the answer in any order. So what does this all mean? Let's take a look at the first example here. So our input array is 2, 7, 11, 5, and our target number is 9. And the output will be 0 and 1. And the reason for that is because the 0th element and the first element add up to 9. And no other elements add up to 9. So in this case, we have to return an array where the indices will be 0 and 1. But according to this, we also could return 1 and 0. It doesn't matter. The next important part of this description is that we cannot use the same element twice. So in the case of this little example that I scribbled up here, we have an input for 4, 5, and 3, and our target number is 8. So in this case, if I took 4 twice, this would add up to 8, right? But in that case, the output would be 0, 0, which is invalid according to this problem statement. So what is a valid solution in this case? So since I cannot take 4 twice, but I can take the two other elements, 5 and 3, they also add up to 8, and they are different numbers. So in this case, one valid solution would be 1 and 2, and another valid solution would be 2 and 1. The next important part of this problem statement was that there is exactly one solution. So in this second example, we have 4, 5, 3, and 6, and our target number is 9. So how can these numbers add up to 9? For example, one solution would be 4 and 5, but there is another solution, 3 and 6. So since there are two valid solutions for this problem, this is invalid. We don't have to consider this during the implementation. What is the most intuitive solution here? I think if we start pairing up the numbers one by one and check whether they add up to 10, we would find one answer. So let's try this out real quick. We have to start with the first number in the array, and moving forward, we pair it up with all of the other numbers. So the first one is 1. Do they add up to 10? They don't because it's only 4, so we have to move forward. Next one, 2. They add up to 5, which is still not 10. Next one is 4. They add up to 7, which is not a solution. Next one, 6. They add up to 9, so that's not good either. What is the next step that we have to make? We move this pointer to the next number, and we start comparing the other numbers with this number. One question is, do we have to add 1 to 3? We don't, because we have already done that comparison, right? That was part of the previous iteration. We only have to move forward. So we have to add up 1 with 2 first, which will be 3, which is not the target number. Next one, 4, 6. We haven't found a solution yet, so we have to move yet again. The next start position will be 2, and we agreed that we don't have to move backward because we have already made those comparisons. So the first number is 4, this will add up to 6, that's not the target number. Then 6, it still doesn't add up. But the last comparison that we're going to make will start from 4, and we add it up with 6, which will yield our target number. So the output will be 3 and 4. So I hope you get the gist of it. We are basically adding up all the elements with all of the other elements and try to check if they add up to the target. If they don't, we move forward. If they do add up, then we can just return because we already found that one valid solution that we're looking for. What will be the complexity of this solution? So time-wise, it will be big O of n squared. And the reason is we always have to find a number we start from, and then we have to iterate through all of the numbers after that to compare it with. And space-wise, this is going to be constant space because we are not using any additional memory apart from these two variables that we're moving with. This is not a very efficient solution because of this time complexity. It will ramp up very quickly if we have hundreds of thousands of elements, and it will take a lot of time to find those two numbers that add up to the target. We should start looking for a better solution that will decrease this time complexity. In the previous example, we had to check if the numbers add up and we always had to be moving. But what if we sacrifice some of that precious space complexity in order to have additional information readily available, and we don't want to iterate through the array so many times? For example, maps and dictionaries are perfect for this situation. They have constant access and insertion times, so we can save a lot of time on that. They store keys and values, and we could keep track of the already seen elements if we store the keys as the numbers and the values as the indices. Alright, let's see this in practice. It will make sense. Let's take each individual number from this nums array, subtract them from the target number, and look for that particular number in the map. If that number is present in the map, then we know that we found a match. So let's start with the first one here. The first item that we're going to check is 3. So 10 minus 3 is 7. 7 is not present in our map yet, which means that we haven't found a pair that we can use. But we have to store this element here in order to reuse it later. So we say that we're going to put 3 as the key and 0 as the value because 0 is the index of this element. So the next element is going to be 1. 10 minus 1 is 9. This is not part of our map yet, so we can't do anything with this, but we can put 1 into the map with the index of 1. Our next element will be 2. 10 minus 2 is 8. This is not part of our map, but we have to put 2 in the map with the index of 2. The next element is 4. 10 minus 4 is 6. This is not part of our map, but we put 4 with the index of 3. And the last element that we have here is 6. 10 minus 6 is 4. In this case, we found a match in the map. We know that for 6, we already have a pair that we can use for the solution. So how will the solution look like? In this case, we know that the index of 6 was 4, so that might be our first element. And we know that 4's index was 3, so we use that. And that's it. What will be the complexity of this solution? Time-wise, this is going to be big O of n, because we only have to iterate through the array once, and we only touch each element once. But space-wise, this is going to be big O of n as well, because potentially we will have to store each and every element in our map. So 3, 1, 2, 4, and so on. This is a much better solution time-wise, but we also have to consider space complexity, so it kinda depends. If we have millions of these items, it might add up, but much faster than the previous brute force solution. Let's try to code this up real quick. So we want to create a map that stores integers. And after that, we are going to iterate through this array. and take the difference of this new element and the target, and check if this difference is part of our map, because if it is, then we found a match. So the elements of this return array will be the two indices. And after that, we are just going to put this new element into the map with its index. And that's it, we can return null. Ideally, this should not happen because there is exactly one answer guaranteed, but we have to return something anyway, so it will be null. Thank you for watching. If you found it helpful, please hit the thumbs up button and subscribe. Leave a comment or a suggestion, it's very much appreciated. See you next time, bye bye.